Hello everyone, welcome to lecture 4 of week 11 of the course Power Network Analysis. We are continuing with our discussion on the last module, which is transient rotor angle stability analysis. In short, I have intentionally kept it simple as stability analysis. And in this discussion, we will continue with the aspect of swing equation, which is analogous Newton's second law of motion for rotating synchronous machines, specifically from the rotor perspective. And this is going to be the second ongoing lecture in terms of swing equation. We have discussed about the basis of swing equation in the previous lecture. So what we discussed or understood in the previous lecture was that every synchronous machine, the associated rotor rotates at a synchronous speed under steady state condition, during which the input mechanical power and electrical output power, they both match each other, they balance out each other, assuming the losses to be negligible. So the associated acceleration torque, which is difference acceleration power, which is difference of PE and PM and PE, turns out to be 0, and hence under steady state condition the associated rotor angle, which we inherently coincide with the internal EMF of internal angle of the internal EMF of the synchronous generator with respect to terminal voltage. That corresponding double derivative tends to be equal to 0 under steady state, and hence the rotor rotates at synchronous speed with respect to the stationary axis on the stator, or alternatively the rotor speed and the rotating stator MMF in the air gap, their relative velocity is 0 because both tend to rotate at the same synchronous speed as dictated by the operating frequency f and the number of poles in the synchronous machine. And we have understood in the synchronous generator module that the number of poles induced on the stator and number of poles induced on the rotor correspondingly by the corresponding MMF, they turn out to match each other. And we had concluded our last discussion with the assumption or with analysis. In fact, there are several assumptions involved in transient rotor angle stability analysis. One of the assumptions being that network dynamics or network damping is neglected. The change in mechanical power, input mechanical power or input torque is doesn't exist because the associated turbine and governor dynamics are very small compared to the transient period of study in which we want to analyze the stability problem. And additionally, we also had this angular momentum term defined M, which actually is a product of J, which is the angular momentum J of the rotor and turbine combined together, multiplied with omega S, which is actually the rotor speed in terms of the rotating reference axis. We had assumed this M to be a constant quantity, and hence we assume that M is equal to J omega Sm, where omega Sm is the mechanical synchronous speed of the generator, which is a constant for a given frequency and number of poles. Whereas on the other hand, the actual swing equation, it consists of term J omega S instead of M. And this assumption of choosing omega S to be equal to omega Sm in terms of defining this constant M works well for transient rotor angle stability analysis and helps in analyzing our actual effects on rotor more effectively. Although, practically speaking, if one doesn't want to have this constant M assumption and choose J omega S instead of M, one needs to have detailed analysis, because then we'll have different multiple variables appearing in on the right hand side, where omega S will also be a variable, delta M will also be a variable. So corresponding numeric equations to solve those equations may be different. We'll not discuss those details at length. We'll keep our discussion simple, because the intent of this module is to apprise all my students about the basic concepts of how transient rotor angle stability analysis can be done in the first place. There's an alternate constant defined instead of m. We call that constant to be h constant, or also known as inertia constant, which is a ratio of stored kinetic energy in megajoules at synchronous speed in the synchronous machine divided by the individual rating of the machine in MVA. And its unit turns out to be in second. Why? Because if you see the ratio of H is energy divided by power, whose unit is MVA or megawatt. And as we all know, power is nothing but rate of change of energy, or let's say if E is the energy and T is time, then the corresponding ratio of H would turn out to be E by P, which is also analogous to E by T, which is only left with a dimension of time T, and hence its unit is in terms of constants. And if we correlate the stored energy in terms of the angular momentum J and the actual synchronous speed of the machine defined as omega Sm, S max being the machine rating in MVA, we can define, and since M is nothing but J omega Sm as we have discussed here, so inherently M is equal to 2H into machine rating S max divided by omega Sm. So we can substitute M in terms of H, where machine rating is anyway known. Omega Sm is the actual synchronous speed of machine, which is also known for a given machine. And H in a way is a representation of M, which indicates how much of kinetic energy is stored or can be stored during disturbances with ratio to the machine rating. So if we represent M in terms of H, this becomes our analogous swing equation in per unit, because on the right hand side we have power whose unit was watt, and then we have also S max whose unit is also watt, with a multiplier obviously, so those multiplier terms can get neglected, and basically watt by watt is essentially nothing but per unit. So maybe towards the end of the lecture of this particular module, in fact the last lecture of this module, we'll understand at length the importance of this inertia constant H, specifically in terms of renewable energy integration. But just to apprise you or highlight the importance of H in terms of different generating resources which are connected to the power network from the transient rotor angle stability perspective. If we have resources which are non-rotating in nature, for example, solar PV plant, solar PV panel, solar PV plant, battery energy storage systems, and related static devices, then what essentially is happening from the power network perspective is that from the overall inertia constant of the entire power network, or at a point of interest where H constant is to be evaluated for a given node or given point in the power network, if more and more generation capacity is pushed into the network, what happens is H being proportional to the stored kinetic energy divided by the generation capacity or machine rating in general. With more and more generators being pushed in, the overall generation capacity of the system tends to go up. But with no rotating devices present, specifically for solar PV and battery energy storage systems, there is no rotating part. So these generators in a way cannot contribute anything to the kinetic energy which is already present in the network. So what happens is that with more and more static or non-conventional generating resources with no capability of directly being able to store kinetic energy, only the generation capacity tends to increase, kinetic energy more or less remains same, and as a result, with more and more renewables being pushed in, the H value tends to go down. The overall effective H tends to go down. And with reduction in H, what could be the problem that one can anticipate? The answer to that lies in this particular question, that let's say we have a unique disturbance which is happening in two scenarios for a power network. In one scenario, the power network doesn't have many renewable energy resources connected to it, specifically solar PV and battery energy storage systems, which tend to reduce the overall H. That is one scenario. And in the another scenario, our power network has high penetration of solar PV and battery energy storage system, in which the effective value of H tends to go down. So if the same disturbance is happening at some point, and we are trying to find the overall transient rotor angle stability analysis, specifically from the perspective of this rotor angle delta, which is being measured with respect to the rotating reference frame in the synchronous generator or analogous synchronous generator, then since the disturbance remains the same, the RHS quantity will more or less remain the same in both the scenarios, be it with low penetration of renewables or high penetration of renewables. With high penetration of renewables, the problem is that the RHS term or the disturbance term, because mechanical power is not changing, so it will remain constant. The only term which would change is PE. With same disturbance, the RHS effective term would remain the same, but with high renewable penetration, as discussed here, the value of H would go down. So it is likely that the corresponding double derivative term sitting over here will take up a higher value in case of higher renewable integration, specifically solar PV and energy storage systems, compared to a case where renewable integration, specifically solar PV and energy storage system, is lower. Because in that case, the corresponding H value would be higher, and with the same disturbance, RHS term more or less remains the same. So the LHS products, they would balance out each other, and with lower value of H in case of high solar PV and energy storage, the corresponding double derivative term will tend to take a higher value, which increases the chance of having more worrisome cases in terms of delta angle having more deviation or lesser deviation compared to a case where H value is higher with in terms of lower renewable energy integration. So we'll discuss this aspect specifically in the last lecture of this module. So please have patience with that. But I just wanted to highlight the impact of renewable energy integration on the value of H and the corresponding issues that might come up in terms of transient rotor angle stability. Coming to our equation here, I have reduced omega Sm or rewritten omega Sm in terms of omega S here, where I'm intently removing the notation of M here. Basically, it should be M here because omega S M or omega SE, they pertain to respective mechanical or electrical synchronous speed of machine. And since we are talking about the equation in terms of per unit, so both omega Sm and omega Se in per unit will turn out to be the same value. So we have removed the intently the notation of M, indicating that omega S is the corresponding synchronous speed irrespective of mechanical or electrical domain. And delta being the associated rotor angular displacement with respect to synchronously rotating stator MMF. So if in terms of given frequency, as I mentioned, omega S is nothing but 2 pi f. So if we substitute omega S as 2 pi f here, then our corresponding swing equation is in terms of H and F, and the remaining terms, they remain the same. Interestingly, every synchronous machine or every bus in the power network can have this emulation of corresponding swing equation. Specifically for synchronous machines, we'll keep our discussion simple. Every synchronous machine connected to the power network will have such a swing equation, and this swing equation, which is a second order equation, can be broken down into two individual first order equations, where d delta by dt is defined as omega r, where omega r is the relative angular velocity of the rotor speed with respect to the synchronous speed omega s. Omega is the actual rotor speed with respect to the rotating axis in the synchronous machine. And the double derivative d delta square by dt square will become d omega r by dt. So the solution of these swing equation, be it the double derivative form or the first order differential equations, if we solve these equations for fixed PM and varying PE, we'll get an expression of delta or omega and omega r in terms of time. And this swing equation essentially is the variation of rotor angle with respect to time, and that's why we also call this plot or analytical plot to be the swing curve of the machine. Inspection of this swing curve for different machines, it indicate whether these machines would remain in synchronism. That means the rotor angle differences, whether they will retain the same steady state value or whether they would increase or decrease with respect to a particular disturbance sort of premised by an initial operating condition. So to analyze these different swing equations for respective machines, the way we converted all our electrical calculations with respect to a common system base, conversion of these H values to a common system base is also important. And how does this change happens, or how does this base quantities match? The answer to that lies in the definition, or in the uh, um, definition of H itself. So H and S mac, they are inversely proportional. So for maintaining the same system base, if I have to convert the machine H in terms of a common system base MVA S base, then I have to essentially maintain the product of H mac and S mac, because H and S, they are inversely proportional. So the product should remain uniform, and that's how this conversion of H can be made for respective machines on a common system base. For a large system with many such synchronous machines, the number of swing equations would accordingly be more and more for large synchronous machines. So can there be ways of reducing the number of swing equations so that the computational time or effort involved can be minimized? So yes, there are different ways of reducing such number of swing equations. The first set of reduction comes from the aspect that there will likely be synchronous machines which tend to swing with respect to each other. That means their rotor angle variations or their respective swing curves after a disturbance follow a similar pattern with respect to time, or follow a similar trajectory, and we tend to call those machines to be coherent machines or swing machines, because their variations or their response to a disturbance is more or less same. So if we can identify such swing equations on machines, there are ways of identifying such coherent machines. There are different studies involved with that. We'll not discuss those at length. But suppose we identify such a set of coherent machines, where these coherent machines are maybe 2, 3, or 4 in number. We'll consider the case of 2 such machines which are incoherent with each other. And each of those machines, machine 1 and machine 2, have their respective swing equations respectively defined, and the rotors, they are mechanically sort of responding together. So we can reduce these 2 swing equations because their rotor angles are deviating or varying in the same pattern. So we can combine these 2 swing equations. Basically, we can add these 2 equations and get an analogous swing equation which is together replicating both the individual swing equation, and that's one way of reducing 2 swing equations to one single swing equation. If the number of coherent machines is more than 2, then we'll have additional terms coming in, like as H3, H4, H5, as many number of swing equations we can get for respective Hs, similarly for respective PMs and respectively electrical power outputs. So swing equations, they can be reduced for coherent machines into one single equation, but one has to identify these coherent machines a priori. The other set is non-coherent machines, where 2 machines or synchronous machines, their rotor angle variations with following a disturbance are completely different. Their swing curves are completely dissimilar, and we would call those sets to be non-coherent machines. Suppose we have 2 such non-coherent machines, then there is a way of reducing these 2 non-coherent swing equations into one single equation. How do we do? We write, first of all, the respective swing equation of every such non-coherent machine and take the difference of these 2 equations on respective RHS and LHS terms. So basically, delta term is delta 1 minus delta 2. So we are basically subtracting second equation from the first equation, and we can write one common swing equation for 2 non-coherent machines, where HEQ, PMEQ, and PEQ are respective H input mechanical power and electrical power output equivalent terms as defined in terms of individual machine constants H1, H2, PM1, PM2, PE1, and PE2. So essentially, swing equation, what we have discussed, that if in order to understand transient rotor angle stability analysis, we have to first of all solve these swing equations, and more the number of swing equations are, more can be the time involved. So there has to be ways of figuring out how these number of swing equations can be reduced, because these are differential equations. So essentially, if the machine or the network tends to remain stable, what we would observe is that irrespective of whether the machines are coherent or non-coherent, the rotor angle differences would tend to decrease or tend to remain finite following a disturbance. In case instability happens, this quantity or this aspect won't be true. That means the rotor angle deviations or differences would either tend to go up or tend to go down. They will not remain finite. And essentially, for a respective machine, if one has to understand the transient rotor angle stability perspective, then it is basically a relative property associated with the dynamic behavior of other coherent or non-coherent machines. So, to keep our discussion simple, we will consider uh, uh, three cases essentially, or in fact, we'll start with two cases. We'll first try to understand the transient rotor angle stability of a single machine with finite h constant with respect to the infinite bus. The notion of infinite bus remains the same as we discussed in terms of the context of power flow analysis as well as in the context of economic dispatch perspective or synchronous model perspective. So, we'll consider three cases, starting with case number 1, where we focus on transient rotor angle stability of a single synchronous machine and rest of the network being represented as an infinite bus. Then, having understood case 1, we'll try to move up to case 2, where we try to understand the stability phenomena between two non-coherent machines with finite h constants. They can be coherent or non-coherent. So, I have written for the case of swinging with respect to each other. The discussion that we will follow for second case can also be applied to two non-coherent machines. And lastly, we will take up the most complicated case of multi-machine stability analysis, where definitely we will have to go and use some numeric integration technique. The beauty or importance of the first two cases is that there are ways of avoiding this numeric integration perspective. Why numeric integration is necessary? Because there are differential equations involved, and these differential equations will be solved through numeric integration, specifically for case 3. For the first two cases, the concept of numeric integration need not be understood, need not be applied. Without numeric integration, cases 1 and 2 can still be analyzed, and any stability or instability can still be identified. So, we will start with a simpler case and try to complicate or go to further complicated cases as the cases progresses. So, in terms of swing equation, there is also another important equation known as power angle equation. So, for a synchronous machine, from the transient rotor angle stability perspective, mechanical input power would remain constant as the transient time period is comparatively smaller compared to the response time of AGC. So, the governor dynamics are all ignored or neglected. AVR action is also neglected. At steady state, both these powers, input power and output power, are same, so rotor rotates at synchronous speed. As disturbances happen, specifically electrical disturbances, the corresponding electrical output power would vary, which would lead to a non-zero value of the acceleration torque irrespective of Pm remaining constant. If Pa is positive, the rotor would tend to accelerate because d squared delta by dt being proportional to Pa. Positive Pa rotor would accelerate. For negative Pa, rotor would deaccelerate. And this change in electrical power, as I mentioned, is due to disturbances happening in the power network, because of which the electromagnetic transients would exist in terms of variations in rotor angle with respect to time, also known as in terms of variations of the swing curve. For this analysis, as already discussed in the assumptions of transient rotor angle stability analysis, every synchronous machine would be represented by its internal EMF in series with the direct axis transient reactance XD dash. So, we won't be considering the buses at which terminal voltages were considered. So, basically in terms of PV buses in load flow, we'll have to go inside the machine terminal and figure out a fictitious bus at which this internal EMF is connected, similar to the way we did for fault analysis module, where instead of XD dash, we had been making use of XD double dash, the subtransient reactance. Since it is a transient study, so the corresponding transient reactance value comes into picture. We'll conclude this lecture with a simple numeric example where there is a synchronous machine given whose direct axis transient reactance is given and the armature resistance is negligible. Machine is connected to an infinite bus whose voltage magnitude is fixed at 1 per unit. The generator is, or the machine is delivering a real power of 0.5 per unit, at 0.8 power factor lagging. At this condition, we have to determine what is the internal EMF or the voltage behind the transient reactance while neglecting the rotor saliency effect. That means the machine we are considering is a cylindrical rotor machine. So how do we do this? Since we know that the machine is connected to an infinite bus whose terminal voltage is fixed at 1 per unit, if we can find the corresponding current which is being fed by this synchronous machine, which is responsible for this 0.5 per unit real power, then probably we can correspondingly find the internal EMF E, which is being measured with respect to the terminal voltage of the synchronous generator. So how do we do that? We first of all find out the corresponding power factor angle, and since it is a lagging power factor angle, the corresponding power which is being delivered by the generator is actually being fed to an inductive load, and hence the corresponding armature current is lagging the associated terminal voltage or the infinite bus voltage by an angle 36.87 degrees. The corresponding current, how do we get? V is given as 1 per unit. We are choosing V at an angle 0 or the infinite bus voltage as the reference for all phasors. So corresponding armature current is now known. With saliency neglected, V being known, which is the reference voltage at the infinite bus, we can actually make use of the transient axis, the transient reactance, direct axis reactance, and find the corresponding internal EMF E dash, which is leading the corresponding terminal voltage. Remember, for generating action, delta will always remain positive, and that is evident here also. So, in the next lecture, we will take up the interesting discussion on how to reduce the power network buses into only buses retained with internal EMFs of the synchronous generators for transient rotor angle stability analysis, which we'll call as Watt reduction. And we'll also take up the first case of transient rotor angle stability problem, specifically for the single machine infinite bus system, which in short we also call as SMIB, S standing for single, M for machine, I for infinite, and B for bus. Thank you.